How do you know what chapters to skip in a book? Well, so for example, sometimes, not always, but sometimes a book will tell you like chapters that you can legitimately skip in a course. Like in other words, oh, and a really good example of this actually that we looked at recently was David McKay's information theory book. So in it, he gives you this big, long big old flow chart of like what you can skip or the dependencies is what he called it. So if we look here at this book, which I've read before, I think it's really good if you're interested in this topic. Um, oh, what? Sorry. He gives a big long flow chart. Look at this. Look at this. This chart about dependencies is real awesome. Yeah, and I think it's going to do this thing where if I move it, for some reason it changes color. So right now it's not moving on the stream, but when as I move this thing on my desktop, as I move this window on the desktop, things are changing colors. You can see it's like flashing different colors. Blacks and whites stay the same. I have no way of explaining that. Don't understand why that's happening. Don't know what to do about it. So just gonna live with it. But you know, usually like another example might be something like, uh, ooh, ooh, that was not good. This representation theory book, this one here. Sorry, this guy. So if you look at the table of contents, you can see that there is a part that's about finite groups. Okay, finite groups being one sort of part of representation theory, and then there's a second part which is about Lie groups and Lie algebras. So like if you get tired of reading this stuff, and I mean I don't know, like you get a sense that maybe this is not necessarily what you always want, what you want at the moment. You really want to get into the Lie group things, you just go right in there. And if they make reference back to stuff that is in a previous chapter and you really want to know about it, then you read it. So I think, for example, when I read through this book, when I looked through this book, or when I used this book extensively, I read chapters 1, 2, and 3. I think I did 4 for a class, or I covered this set of ideas for a class. I don't remember anything about 5 or 6. 7 and 8 and 9 and yeah, well, so like this part 2 here was very was something I studied a bit, and some of part 3, but like at a certain point I think, I don't know where along this, in this part 3 here I got to, but a lot of these things I think maybe also I probably grabbed stuff from here, like Dinkin diagrams I remember studying, although again all of this stuff has fallen out of my ear. Yeah, anyway, you skip around, and hopefully like if they make reference to something that you didn't remember, you can flip back and just take a look at it. But it's not uncommon to be flipping around quite a lot. You definitely don't read it like you definitely don't read a math book like you do a novel. This book I used when I was this book was part of an undergraduate. I got this book from while I was an undergraduate. It was my last year of undergraduate education, and I studied this book with a professor. And I mean, I liked group theory a lot, And so he said, oh, why don't you start studying representation theory? And luckily he knew a lot about that. So yeah, I have no idea. I always am impressed with this copy because this is red. I don't know what that means exactly. It might be that it's like a preview copy. I don't remember if my instructor gave this to me. It doesn't have his name in it, but yeah. I use this in undergraduate. Have I read all of the books behind me? Yeah, but they're not all math books. And I've not read them cover to cover. Yeah, but I'm a boomer. Please remember, I am a boomer. 42 years old. So I grew up in a time when I grew up with books. I grew up with physical books. The idea of reading a book off of your screen was unheard of. But yeah, it's something that I have a preference for sure. I like being able to, for example, sit on a nice chair, open up a book, that sort of thing. I like the smell. I like all that stuff. So having the physical text is it is important to me, and this extends to other things as well. Like I always think it's funny. Zoomers always laugh at me, but like I have such an obscene amount of like vinyl records and CDs and stuff. like I'm not an audiophile, I don't think, or anything like that. I don't have any particular I don't look down on digital music collections or anything. In fact, it's a hell of a lot cheaper. But because I probably spent a tremendous amount of my disposable income in my life on these physical copies of music, which now you can get for pennies. Consume for pennies. So this is the way we boomers live. Oh yeah. Hey, Linux, you please go ahead and ask your question. If I do this, that means you're going to be called up by Streamlabs bot. Next up, Linux 1488. It's all you. So let's see. 24 over x minus 3 minus 6 over x plus 3 is less than or equal to negative 1, right? So my first tip is, you see how these are sort of broken in pieces. Like, can we write this as a single fraction? Can we write these two fractions, which are being subtracted, can we write this as a single fraction? And if so, what's the first step that we need to do? I mean, we can. I sort of gave it away. What's the first step that we need to do to make this into a single fraction? Did I say Linux 1488? I'm sorry. I did watch a Proud Boys video very recently of them talking about each other as true 1488 Proud Boys or something. Yeah, both sides by x minus 3 and x plus 3, exactly. It's not interesting. It's not interesting. 24 times x plus 3 minus 6 times x minus 3 divided by x minus 3 times x plus 3 is less than or equal to negative 1. Okay, so then what we can do is expand this out, collect like terms, and all of that kind of stuff. So then this is equal to 24x plus, oh god, a ginormous, what is 24 times 3? I guess that's 72. Minus 6x plus 18. Is it clear how I did the algebra there? And then downstairs we have x squared minus 9. Is it clear how I did that? Don't I have to multiply the right side too? So no, right now all we're doing is goofing around with the left-hand side. We're not touching the right-hand side at all. Now, please understand, what I've done in going from this step to this step, just to the left-hand side, is I've multiplied this term right here by a particularly fancy version of 1. I multiplied it by x plus 3 over x plus 3. And this guy here, I've multiplied by another fancy version of 1, a different fancy version of 1, x minus 3 divided by x minus 3. And so all I've done was multiply each of these terms by a fancy version of 1. When I do that, the reason that I do that is to make a common denominator so that it's straightforward for me to subtract the numerators, which is what I have here. We really haven't been, so right now, we've really not dealt at all with the inequality aspect of this problem. We're really just massaging this side so as to make it a single fraction, because that will make it easier for us, I believe, to solve the problem. Wait, so it's very straightforward, Linux. It's very straightforward. So let's just take a look. The reason is because whenever you have some, you should, I think that this is a good piece of advice just algebraically. There are certain things that you should just recognize right away. One of those things that you should recognize right away is that when you have x minus a times x plus a, or maybe in the other direction, where a is anything, literally anything, then this is the same thing as x squared minus a squared. This is sometimes called a factorization of difference of squares. This is like the words that are used. This is the words. And a difference of two squares. Yeah, see, why? Why is it a difference of two squares? X squared minus a squared. That's why. You see? Difference of squares. And that's always the same thing as x minus a times x plus a. Now, what is it? Why is this the case? Please understand, it's not just some random fact. It's not just some disembodied thing that came like a bolt from the blue because the experts decided it had to be that way. You can expand out this expression over here on the left-hand side, and I swear to God, you will get x squared minus a squared. So like we can do it right now. Did I lose you, Linux? Sometimes when I go off on these little tangents, I lose people. Okay, you got it. Okay, good. All right, so here we is right here. Let's go back to this and let's collect like terms in the numerator. I remember doing this in 8th grade. Collect like terms. So the 24x and the minus 6x get married and become an 18x. And the 72 and the 18 get married and become a 90. So now what we have is this. What is the best way of going about figuring out when? So now we're going to deal with the inequality here that we see. And I don't know if there's like some systematic way of going about doing this. I don't know. I just know how I know how I would attack this problem. So the way that I would attack this problem is to, instead of thinking about when this is less than or equal to -1, I would instead think about when it's equal to -1, just as a sort of first starting point. Instead of thinking about this inequality, I would first think about when equality happens. And there's a good reason for that, which I will describe in just a moment. But for now, what I want to say is we're going to first consider when 18x plus 90 over x squared minus 9 is equal to -1. So if you were faced with this problem, what would you do? Linux. If you were faced with this equation now, not an inequality, but this equation. I know you said you sucked at equations, but can you think of maybe a first good play that you might make in attacking this equation? I think there's a better first play. Hey, think of it this way. What annoys you about this equation? Is there something annoying about it? I think I can actually take down the Firefox, right? What annoys you about this equation? There's something particularly annoying about it. The big numbers, whatever. It has a bottom. Do you see that it's annoying that this thing has a bottom? If it's in the typical x squared plus x plus a format. Okay, so help me. Help me. What can I do to make this less annoying looking? Look at this fucking fucker. It's a fucker. You know why? We hate its guts. You know why? I mean, I know why. Because it is a... It's a... It's a... Yes, it's a fraction. Not sure what you all were thinking. It's a fraction. And so we want to fix that because we do not like fractions around here, okay? So we're going to multiply both sides of this by x squared minus 9. And if we do that, what do we get? We get 18x plus 90 is equal to negative x squared plus 9. Can we all agree? What's my next play? I know what you mean. Add x squared and subtract 9. So what we get is x squared plus 18x plus 81 is equal to 0. Is that right? That's excellent. We want to see a 0 over here very badly. Oh yeah. We do not like fractions around here. And if we can kill a fraction, we will. Okay? If we can, we will. We don't like them. Does this thing factor? It does. How does it factor? Whoa. Whoa, what? Wait, what? Uh-oh. No, this is a very... Listen, we love everybody. We are very inclusive around here. Oh. Is this some... Is it... never mind. Okay, so let's see. X plus 9 squared equals 0. That's excellent. And so what does that mean about x? we're writing a fine line here. What does this mean about x? X equals -9. Good. So when x is equal to -9, that's the only moment when this expression here is equal to -1. I think what we also need to know, of course, that's not what we're looking for. We aren't looking for places where x is where this expression here is equal to -1. What we're really looking for are places where this expression is less than -1. We agree? No. The Germans pronounce Gaub's name correctly. Okay. Sorry, I just need to pause here. We need to clear this up because this has been a big point of contention here. Germans, back in the old days, used to spell Gaub's name correctly. Like the way that it was spelled is G-A-U-B. But for some reason, I don't know why. I think it's just because Americans, they think they're special or something. They decided to pronounce that name Gauss. Okay? So then Germany, after post World War II, it was a historical trend that all over the world that there was this phenomenon of American cultural hegemony. That what happened in America sort of became the reality all over the world, culturally speaking. And this had its effect on the German language as well. And what you saw was German starting to remove that B from their alphabet, like altogether. So instead of now writing Gaub's name as G-A-U-B, they now write it G-A-U-S-S. And in fact, many Germans now pronounce it in the American fashion, Gauss. But if you are like me and you're a globally minded person, okay, then you prefer the original German, which spells Gauss's name G-A-U-B, and you pronounce it as such, Gaub. In this channel, we honor the German language. All right, so anyway, returning to the problem. When x is equal to -9, we see that this expression is equal to -1. But again, we're not concerned with that necessarily. What we're concerned with are those values of x which make this expression here less than or equal to -1. Okay, so the way we have to think about this is as follows. We have to think about the possible locations where we could go from either being greater than -1 to being less than -1, or the other way around, being less than -1 to being greater than -1. Those moments are going to correspond to one of two types. So here's the sort of model we want to set up for ourselves. Here's the xy plane, all right? And here is the line y equals -1. Now, I don't know exactly what the graph of this thing here looks like. But what we can imagine is that, well, now what we know for sure is that at x equal to -9, we know this is the only spot where the graph intersects this dotted line. This is what we know now. We have to ask ourselves, what are the other possible And this is the location where, this is one location where the value of 18x plus 90 divided by x squared minus 9, where the value of this expression here could change from being less than -1 to being greater than -1. Why? Because this is, it's continuous wherever we draw the graph of this thing. We can draw the graph of this thing without lifting up our pen or pencil, except at places where this thing is undefined. We'll get to that in just a second. But at least at -9, it's possible that the graph does something like this. Goes through that point like this. It's also possible, though, by the way, that the graph does something like this. Or that it does something like this. We really don't know which of the three options we're in. So we have to study it. Now, what I want to say also, Linux, is that there's two other places where we could have a change in the status of whether or not we are less than or equal to -1 or greater than or equal to -1. There are two other places where this could possibly happen. You want to know where those are? Or do you know where those are? So -9 is one, because that was a place where this is equal to that. But there's two other places where we could have a change where that as we go past that value of x, we see the graph going from below this dotted line to above it, or vice versa, above it to below it. What are those two additional values of x? Any idea? Yes, no, not maybe. You're exactly right. Those are the other candidate locations where this thing could change from being less than or equal to -1 to being greater than or equal to -1. Excellent. That's really good. So here's -3 and here's 3. I don't know what's going on there. What I do know is that this expression here is not defined at -3 or 3. They're going to correspond, I don't know if you're familiar with this, they're going to correspond to what are called vertical asymptotes. Now, what have we learned? We've learned that the only possible locations where this expression can change in status are at -9, -3, and 3. That's because of continuity. I don't know where you are in your life, if you've even heard of that word continuity before, but I can promise you that if you don't know it now, you will soon enough. What does change in status mean? Good. So what I'm saying is that these are the places where this thing could possibly change in status, where by status I mean the value of this expression could change from either satisfying this inequality to not satisfying this inequality. It's a little bit difficult to talk about. I think that maybe if we finish out this problem, we can have this discussion afterward, because I want to give you a method now for killing the problem now that we've established these three critical points here. So here's how we're going to do it. Do you notice, Linux, that these 3 points divvy up, that they cut up the real line into 4 parts? 1, 2, 3, 4. Uno, dos, tres, cuatro. 1, 2, 3, 4. 1, 2, 3, 4. So what we're going to do is pick what I'm going to call a test point inside each of those 4 chunks. So let's do this in blue. What is and you can pick literally anything. So let's pick a test point over here. What would you like to pick? What number would you like to pick which lives in this interval? Yes, -10. I like it a lot. How about here? What should we pick in this interval? Literally anything. -4. Okay, let's go. How about in this interval? I mean, you're not allowed to choose anything other than 0, okay? You're not allowed to choose anything other than 0. And how about in this interval? Greater than 3. Just choose 4, okay? Don't be smart. Don't be smart. Just, okay, 5. Okay, that's basically the same. I don't care. Doesn't matter. So what we're going to do is test whether or not this inequality is satisfied. How? By plugging in these values into this expression here and seeing whether or not this inequality is satisfied. So I'm going to write it like this: test point. And then I'm making a table. Look at me. I'm making a table. Test point. Inequality satisfied? Question mark. So at x equal to -10, for example, is the inequality satisfied? Only one way to check. We have to do arithmetic. Now I'm dumb. So let's see. What does the numerator look like? I don't care about the exact value though. What does the numerator look like if we put in x equal to -10? Does it feel oh no, oh fuck me. We have to do less than -1, don't we? I probably did this badly. I should have moved the 1 over, shouldn't I, people? It's too late. It's too late. I fucked up. Oh well, okay. So yeah, I actually do care about whether it's how negative it is. I need to know how negative it is. So let's see. Let's do the arithmetic here. 18 times -10 plus 90 divided by -10 squared minus 9. So upstairs we get -180 plus 90, so that's -90 divided by -190. So this is equal to what? You didn't see any of that? That's 100, people. Is this 99? 91, I mean? I have no idea what I'm doing. Is this arithmetic correct? Can you help me? No, I'm not okay. You kidding me? What's happening here? Okay. And is this bigger than or equal to -1? Sorry, is this less than or equal to -1? So is this inequality satisfied at -10? No, it's not. Yeah, I'm not good at arithmetic. You think? Okay, whatever. X equal to -4. We play the same game. So what's 18 times -4? Plus 90. Oh my god. Divided by -4 squared plus minus 9. I don't know what I'm doing. So what's 18 times -4? Good god. It's like 40, 72. -72 plus 90. Is that 18? Over 16 minus 9? How are we doing? Is the inequality satisfied? Is the inequality satisfied? Nope. How about x equal to 0? So this is easy. We put 0 there and 0 there. That kills these two. So we get positive 90 divided by -9. And that's -10. I know that one. And so is the inequality satisfied? Yes. And one more thing to check, x equal to 5. So let's see. It's pretty clear, right? If x is equal to 5, the numerator is positive and the denominator is positive, right? Both are positive, so the quotient is positive. And so we can't possibly satisfy the inequality. No. I mean, yes. No, I mean, no. Sorry. I think what I wrote is correct. So what is the conclusion? The conclusion is as follows. Conclusion. So for example, the conclusion from this factoid right here about x equal to -10, not satisfying the inequality, is that if x is in the interval from -10 all the way up to -9, the inequality is not satisfied. That, in other words, this is sort of what I was trying to explain before. By testing a single point, you can deduce something about an entire. What have I done? I'm sorry. I'm losing my mind. It's from -infinity to -9. If x is anything less than -9, then the inequality is not satisfied. And you know this just by testing a single point in that entire interval. And this is because the only possible places where the answer to this question, is the inequality satisfied, the only possible places where that question could change from a no to a yes or from a yes to a no are at these places where either this expression is equal to -1 or those places where the expression is undefined, where there might be a vertical asymptote. These are the only locations where this can happen. What we've learned is that if x is in this interval, then the inequality is not satisfied. Similarly now, because of the x equal to -4 thing, we now know that if x is in the interval from -9 to -3, the inequality is not satisfied. If x is in -3 to 3, the inequality is satisfied. And finally, if x is equal to 5, if x is in, I feel bad about myself. If x is in the interval from 3 to infinity, the inequality is satisfied. Not satisfied, I mean. Oh boy. Now, there is some question still about what's going on at these points, -9, -3, and 3. So we know that this expression is not even defined. This one is not defined at -3 and 3. So obviously, this inequality is not satisfied at x equal to -3 and 3. But there is still a question about what's going on at x equal to -9. Is this inequality satisfied at x equal to -9? Is the inequality satisfied at x equal to -9? Yes. So the final answer is that inequality is satisfied if x is equal to -9 or x is in the interval from -3 to 3. Let's verify. I have no idea if the work that we did is right because it's long and complicated and I feel a lack of confidence in myself. So what we are going to do is we are going to go and look at Desmos.com, which you should use if you've never used it before. It's very handy, very fast. It's slick. We are going to graph the we're going to graph this function. We're going to graph 24 over x minus what? X minus what? X minus 3 minus 6 divided by x plus 3. And we're also going to plot in the line y equals -1. So look. Notice that as we discovered, the only place where these two curves, the red curve and the blue curve, the only place where it intersects is at -9. And we've also discovered that the only places where this graph is below the horizontal line is between -3 and 3. So you know what? We did it. We win. Does it feel good? Is there anybody else in the queue? Cicero 4259, are you there? Does it not intercept at -9? It intersects. No, it does. The line intersects. Where is my Desmos? Did I flip away from it? Oh no, it's in my Firefox. Less or equal, yeah. So if you look at -9 right here, it intersects. Cicero 4259, you out there? Yeah, at those places, what you have are what are called vertical asymptotes. So if we take a grander view of this graph, and maybe if I even I can plot the lines. X equals -3 and x equals 3. What we see, this is particular to rational functions, is that these are vertical asymptotes. What is a vertical asymptote anyway? It is a vertical line, hence the word vertical, for which the graph of the function gets closer and closer to as we get closer and closer to the x value of that line. Yeah, so x is equal to -9. Oh. X equals -9, or x is equal to, or x is in -3 to 3. You see, those three locations, -9, -3, and 3, are the only places where the status of whether or not the inequality is satisfied can change. Those are the only locations where it can change. And once you know the only locations where it can change, you can then do this test point game to make the problem of solving the inequality into arithmetic. And arithmetic is hard, but it's doable. Particularly if you have a calculator, you know. Well, go ahead, so say we all. It doesn't matter, I guess, because nobody else is in the queue. So if you've got a question, please share. I don't know if there's anything wrong with my bot, but whatever. You feel like the proofs are so lame and it's not satisfying. Because it's sorry, it's drudgery. Actually applying stuff is lame. But there is a lot to be appreciated, I would say, just in the definition itself. Because the definition itself, I think that that's actually quite beautiful. The definition, the epsilon delta definition of limit is actually quite beautiful. Derivatives are quite beautiful. Integration is incredibly beautiful. And the interplay between all of these things is incredible. Calculus is amazing. But the way that, because it's such an, it's thought of as an incredible, a lot of its value to, say, the normies out there that like doing things like designing bridges and making sure the buildings don't fall in a thunderstorm or something like that. The result of that is that it gets drowned out in the application of these ideas. So like you learn about the derivative, if you learn about the story of the derivative, that can nourish you intellectually for the rest of your life. But what they want out of you is not just that nourishment. They want you to be able to, like, you know, do the 30 derivatives using the mixture of the chain rule, the product rule, and all of that kind of stuff. In other words, they just want you to do it, to show, to prove that you understand it in the context of these problems. So they want you to demonstrate your knowledge of the epsilon delta stuff. And if you already feel like you understand it, and you feel like you've had your fill and you're ready to move on to something new, then yeah, it can be a pain in the ass. It's not fun. So, but you know, what else is new? Hopefully, that will change for you. Hopefully the problems themselves, as you keep progressing in your education, will become more and more interesting. That has been my experience. Devil honor. Oh, is that devil honor? Let's go. What are my thoughts about real analysis during undergrad? You know, I have, and what are my thoughts about Baby Rudin? I have Baby Rudin downstairs. It hasn't migrated its way upstairs because I have strong feelings about that book. Just that, I mean, strong sentiments attached to that book. So I did well in the real analysis sequence and all of that, but I don't think I couldn't say that it was the most enjoyable experience for me overall. It didn't agree. So like I think that the terseness of Rudin, I think that left a lot to be desired from me. I wanted more. I wanted more kind of intuition, I guess, around it. That I think at the time I was not prepared to build for myself. But I did work really, really hard in that class, in that sequence. I mean, that's what it demanded of me. It was by far the most difficult class that I had taken, or a set of classes that I had taken, was the real analysis sequence as an undergrad. I thought it was really hard, personally. I thought the exercises were really hard, too. I mean, I really worked hard on those problem sets. And tests. Oh, man. I studied really, really hard. Like, I never had to study nearly that hard with algebra. For some reason, it just was very agreeable to me. I had taken an abstract algebra sequence. Now, I know there are people that are just the opposite there. So I don't know exactly what that is. I mean, yeah, I think there's brains just work really differently in different people. It's kind of incredible. It's awesome that that's the case. But for me, analysis was not traumatizing. It's not the right word, but it was a difficult experience. Is real analysis before complex analysis? I think it typically is, but I don't know if that's necessary. Yeah, I eat corn on the cob horizontally, like a civilized individual. I don't do this. This is insane. This is simply you have to be deranged to do something like this. You have to be deranged to do something like that. Yeah. It's correct. This is the correct way. Bing. Bing, etc. This is typewriter memes. You're all too young. You don't get anything. You don't get my references. It's fine. Yeah. Okay. Great. I was doing my best impression of a typewriter. See? You Zoomers, you're not really sure what a typewriter is. Yeah, well the other possibility that I was thinking that could reflect some kind of mathematical proclivity would be like you chew around in sort of a spiral while you're doing a simultaneous horizontal and sort of rotational motion. I always imagine that being analogous to like a torus knot or something. So like maybe this is how a topologist would do it. Oh my god. Just sort of like scrape the kernels, hopping them into your mouth. And yeah. Yeah. Anyway, the world is agreed. The only civilized way to do it is just to go like that. Okay. Everything else is weird, deranged, probably need to be put into some sort of, you need to be given some treatment of some kind. Oh, corn on the cob is really good though. I really like it. It gets stuck in your teeth. It's great. NWXNK. What up? If anybody else has a math question, type !join to join the queue. What would you like to know about quaternions? Just sort of what they are? I mean, I can say what they are. I can also say maybe why. Well, I know what they are. So what they are is a number system of some sort. The specific word, the more specific phrase is that it's a normed division algebra. There are normed division algebras, other normed division algebras that you are probably much more familiar with, like the real numbers and the complex numbers. Now, when I say the word real numbers, perhaps if you are a geometrically minded person, what comes into your mind, what you see in your mind's eye, is a real line. Is a line, right? The horizontal line that we all use as sort of a geometric model for the real set of real numbers. Similarly, when you think of complex numbers, if you are a geometrically minded person, the first thing that pops into your mind is the complex plane, two-dimensional. So two real dimensions, right? There's the real axis and the imaginary axis, so-called, in the complex numbers. So what the Quaternions are a four-dimensional number system. A four-dimensional number system. So you have a real axis. So you have the real numbers sort of in there. You have an imaginary, an I-axis, I times the reals in there. But you have two more axes, which are orthogonal to both of those, which are the J and the K axis. It's hard to picture, right? So real easy to picture. Complex plane, little bit more cognitively demanding, but God, haven't we been drawing planes our whole life? So that's not a problem. Complex is easy to visualize. Quaternions, though, four-dimensional, that's hard to visualize. Nobody has an easy time with it. But we just have to come to grips with that, okay? Everybody just has to come to grips with that. What's the way out? The way out is to work analytically. What do I mean by that? I mean, like you write down equations and shit. Like lots of equations, lots of symbol pushing and all of that kind of stuff. That's what Quaternions are. Now, you might notice something conspicuous about what I just said. That there's a real number system, that there's a number system on the one-dimensional line. There's there's a number system on two-dimensional plane called the complex numbers. There's a number system on four-dimensional space called the Quaternions. What about 3? What about 5? Why am I not talking about these? Well, it turns out that there's no analogous number system on these spaces. And actually, the main dude who's associated with Quaternions historically is this guy named Hamilton. And Hamilton was his mission in life was to generalize complex numbers to 3 dimensions. And he was struggling. He was struggling with this problem. And every night he would come home after a long day's work of trying to put a number system on 3-dimensional space. And his little boy would go up to him and say, "Daddy, have you put a number system on 3-dimensional space yet?" And he was a broken man. And he had to look his son in the eye yet again and say, "No, son. I have not yet put a number system on 3-dimensional space." Then he was walking around, no doubt, crushed, beaten, a beaten man walking the streets of London? I don't know. Thinking about his problem. And then, like a bolt from the blue, he realized, I may not be able to do this in 3 dimensions, but I can do it in 4 dimensions. And he invented, in that moment, Quaternions. He invented them. Did he discover them? I don't know. Whatever. He invented the Quaternions in that moment. And he was so hype from his discovery that he chiseled it into a bridge. And you can go see it. I don't know where it is. Ireland? Isn't that the same thing? Basically, right? You can go see it if you want to. And in fact, he was basically right. I mean, his quest to put a number system on 3 dimensions was futile, because later on, maybe 100 years later, it was proved that you cannot. The essential reason why you cannot is something called the hairy ball theorem. It's essentially the statement that the sphere, the two-dimensional sphere, is not parallelizable. You cannot take a hairy ball and comb it continuously in such a way that every hair is tangent to the ball. But it turns out that in 4 dimensions, the analogous statement is in fact the truth. The truth that you can the tangent bundle is trivial. No, not in 6 dimensions. It doesn't happen again until 8 dimensions. And that's because S7 is parallelizable. Yeah, I think there's some weird thing about 16. I can't remember. Yeah, that's the pattern. Like you have to keep on dropping over and over again. So like complex numbers, well, everything's nice with complex numbers. They're gorgeous. But quaternions, what you lose is commutativity. Quaternions are no longer commutative. And if you go to dimension 8, they are no longer associative. The numbers, the number system there. It's gross. And then like, I don't know anything about the 16. There's some, I don't know. There's some way in which like you can have 2 copies of the octonions or something. You know Lie algebra. No, you know cross product. You know the cross product of two vectors in R3. That's not associative. Oh, subtraction is not associative. Division is not associative. Exponents are not associative. I hope the words that I'm saying are right. All right. I don't know. There's something more to say, I'm sure, about quaternions, about how they do rotations and all that. But you know what you really should do? You should look at the 3 blue 1 brown video on quaternions because it's really good. It's super excellent and explains things way better than I could. He doesn't dramatize it as nearly as well as I just did because that was a godlike dramatization. I know that. You don't need to say it. But if you check out 3 blue 1 brown's video, I think you'll be quite enlightened about quaternions, okay? Consecu. You're up. H. Named after Hamilton. H. A pyramid water tank with height 4 meters and base 2 by 2 meters. It's like 3 feet, right? The tank is fully filled, and when the tap is opened, the rate is 1 meter per hour. Decide how long it takes before the tank is empty. Aha. So really the key thing here is to figure out the volume. Do you know a formula or a fact about the volume of that pyramid tank, water tank? So it's always helpful to draw a picture for me. So we have something that looks like this. And then, oh, this is not the best picture, but should have drew it more foreshortened. So I believe that the formula that I know is that the volume of something like a coned off, so a volume of something like this is 1/3 the area of base times height. And the area of the base here is what? So if this is 2 meters, the area of the base here is 4 meters. And what is the height of this guy? It's also 4 meters. Good. So I guess we get 16. Oh, I'm sorry. And I messed up. Hey, look, I messed up. No. I messed up. Because the area of the base is 2 meters. 2 meters times 2 meters. So it should be 2 square meters. 2 square meters. And then, so we get 16 over 3 cubic meters. So that's the volume. Now, we are told that the tap is opened at a rate, and the rate is 1 meter per hour. So I assume that when you say that the rate is 1 meter per hour, I assume that what you really mean is 1 cubic meter per hour. Confirm or deny? Yes. Good. So then how long does it take to become empty? Well, if we have 16 over 3 cubic meters that we need to get through in order to empty this pyramid-shaped water tank, then we can calculate the time that it takes by doing 16 over 3 cubic meters divided by 1 cubic meter per hour. And what I want you to just observe about this is how the units work. Because if you know how the units work, you'll never be at a loss for how to do like a more complicated problem. So the reason you can think of it this way is because, well, we know by rules of fractions, if we take the reciprocal of this, what we get is, well, still 1. The number bit is still 1, but now it's 1 hour per cubic meter, right? And what's neat about this is that the meters cubed here and the meters cubed down there in the denominator, they cancel. And then what you're left with is 16/3 times 1 hours. And there you go. That's the answer. I don't know. We could probably figure out how to realize one face of it as the graph of a function and then do a triple integral. I'm sure that's overkill. I'm sure there are more classical ways of doing it. Certainly the way that occurs to me, though. Okay, Conte Q. Hey, anybody else got a math question? The queue is cleared. So if anybody else has if anybody else does have a math question, just go ahead and ask. Okay, I'll be here. I'm here for the next couple hours. I need a hard-hitting card. Exclamation point join. These are all not hard-hitting. Oh, Elias the Crafter. Let's go. You. Lazuker. Thanks for the follow. Elias, you there? I guess you're typing your question. I'll give you a sec. What is the most straightforward way to prove that the area is 1/3 the volume? The area times the height. Yeah, I don't know. I don't know how to answer what the most straightforward way is. Like, the way that occurs to me is definitely calculus. And I've probably, if I ever learned about other ways of doing it, I've probably thrown them in the garbage. Because calculus is such a kill-all weapon. You know? When is a series uniformly convergent? So maybe maybe I'm mistaken, because I don't know all the real analysis. But I thought uniform convergence. So I assume, okay, yeah, sorry. You're talking about like a series of functions, right? Like you're summing up a bunch of functions. Yes? Elias? Well, sometimes, okay, good. So I just got confused because sometimes I think about series as they are conceived of, let's say, in Calculus 2, where it's just a series of numbers. And then maybe you talk about Taylor polynomials or Taylor series or whatever, or power series. Anyway, doesn't matter. So you want to contrast uniform convergence with a competing notion of convergence called pointwise convergence. So pointwise convergence, I think, is pretty naive. The idea is that for every point x, let's say we have a set of functions on the defined on the interval from 0 to 1 or something like that, and the interval from 0 to 1, and then so we have a sequence of functions, all right? That sequence of functions, which could be arise from looking at partial sums, the sequence of partial sums of a series. So it's okay to generalize to a sequence. That sequence of functions is said to converge pointwise if for every value of x, for every fixed value of x in your interval, the sequence of f1 of x, f2 of x, f3 of x, that sequence of numbers, real numbers now, converges. That's pointwise convergence. So all that's saying is that at any particular fixed value of x, that if you evaluate the functions at those at that point, that you get a sequence of real numbers which converges. That's pointwise convergence. But uniform convergence says that you're not just looking at convergence of at every single point. You're instead somehow taking into consideration convergence over the entire interval all at once. That the idea is that this convergence, or rather the rate of convergence, is sort of more or less the same over the entire sequence, over the entire interval 0, 1, right? So you choose an epsilon. Yeah, this is what learning balance is saying. You choose an epsilon over which works for the entire interval, regardless of the value of x, for which will satisfy this limiting condition, the typical one, that the distance between the nth function and f, that distance is less than epsilon, but that's true for all x in the interval. I'm not sure if I'm explaining myself well, but yeah, this is the idea. And this is the classical example that learning balance is talking about. You should think about with that example that learning balance is saying, that sequence of functions, you should think about whether or not it is pointwise convergent, or what it pointwise converges to, and what the uniform convergence looks like of that sequence of functions. Yeah, one is a problem. One is a problem. I don't know what SK combinator calculus is. Yeah, we played the natural number game, but it was Twitch poison. There were exactly 2 other people that enjoyed themselves while I was doing it. Everybody else was repulsed. I don't know what finite calculus is. Algebraic topology. If one were better at algebra than topology, but one thought topology was more interesting, what should one pursue? Algebraic topology. Algebraic topology is very algebraic and very topological. Just don't ever do topological algebra, okay? Ball was my internet handle for a long time. I've had other internet handles as well. We've gone over them. Wait, isn't it like you can do... I forgot how it works. Isn't it like... Or maybe this is just the name of this... Sorry. Maybe this is just the name of this. Maybe this is just the name of the thing. No, ball is not my internet handle, I don't think. Never mind. Sorry. Sorry. Rather, ball is not my Steam name. You're taking an introductory course in algebraic topology. Yeah, I kind of think so. I mean, like, at some point you're going to be learning homology theory, cohomology theory, all of that kind of stuff. You're going to learn about lots of homological algebra, which is required to understand what's happening in homology and cohomology. So right now you're doing homotopy theory, or rather like the fundamental group and stuff like that, and covering spaces perhaps. Yeah, so I think that the deeper you go into homology, the more, yeah, I think yeah, I bet you that's because of your proclivity toward algebra. Right? There are big algebraic machines at work there in homology. That's a big ass question, but basically so just as a sort of first pass at it, you can think of homotopy as being like if you have two paths, or let's just start with a path. Like let's say you have a space and you have a path in that space. Oh yeah, totally. But it's like the way, for example, the way Hatcher is structured is you do fundamental group and covering spaces and like all of that kind of stuff, right? And then you do big old thing on homology and cohomology. And then there's a section on homotopy theory, like higher homotopy theory, which connects it back with the cohomology stuff. Anyway, so if you have, let's say you have a continuous path between 2 points in a space. Sometimes you're able to deform that path using a, well, let's be a little bit more formal about it, in fact. So if we call this path like, I don't know, alpha, then we can think of alpha as being a map from the interval from 0 to 1 into our space X. X is just some space, don't sweat it too much. But in particular, this is a continuous map. And also in particular, alpha of 0 is equal to this point A, and alpha of 1 is, oh my god, I've lost my mind. Alpha of 1 is equal to B. So you can imagine such a thing. Now, you can also imagine another path, beta, which goes from 0 to 1 into X. And which has the same beginning and end point. So beta of 0 is equal to A, and beta of 1 is equal to B, rather. So you have some other path. Maybe it does that, which goes from A to B again. Okay. Now, suppose there's no hole in the space. So suppose that here, what you could do is, in this case, find a continuous sort of deformation of this blue path to the red path, beta. You can continuously sort of morph one into the other. Yeah? you can continuously deform the blue thing into the red thing using these intermediate green things. These intermediate green thing, what's really happening here is that you have what this is called a homotopy between these paths, between alpha and beta. And if we give this homotopy a name, like we call it F, then properly speaking, what F is a map from, let's say, 0, 1. This 0, 1 cross 0, 1, okay, into X. So what do I mean, first of all, by this cross? I mean that I'm going to take ordered pairs of elements from here. So I'm going to have ordered pair. So the function big F, it eats a ordered pair of real numbers. One from this factor of 0, 1 and the second from that factor of 0, 1. We're going to think of this second 0, 1 maybe as being the time parameter in each of, think of these paths like alpha and beta as being functions of t. So this is t is drawn from here, t is drawn from there. And when t is equal to 0, we have a, and alpha 0 is a, alpha 1 is b. So what we're saying is that when t is equal to 0, alpha of t is a. And when t is equal to 1, alpha of t is b. You can think of it as a time parameter, if you like. If you're walking along this path alpha, for example, then you might keep track of your position at every time t. This alpha is the function which gets that for you. So let's park that t right here. Make this 0, 1 here carry the parameter t. Then the requirements that this be a homotopy. First of all, it better be continuous. This is a continuous map. All of these are continuous maps. Everything's continuous. We're in topological spaces. We need continuity, or else we're not talking about topology anymore. And so if we look at f of 0, comma t, okay? So f is eating the ordered pair of 0, t. What do we get? We should get alpha of t. And if f eats 1, comma t, what should we get? We should get beta of t. So what this big F represents is sort of a continuous deformation of the path alpha and the path beta. And if such a thing exists, then we say that these two paths are homotopic. And it turns out that if you think about the set of all possible paths between alpha and beta, between A and B, if you think about the set of all possible paths between A and B, and you define an equivalence relation on that set of paths, by declaring that two paths are equivalent if there exists a homotopy between them, you get a thing. Okay, so rather, it's useful to think about that. Let's just say it like that. It's useful to think about that. Hi, Scuggett. The homotopy classes of paths between A and B. It's a useful thing to think about. And in fact, this usefulness becomes even more kind of useful if you make the following additional assumption. Suppose A is equal to B. So in other words, suppose you could think about homotopy classes of paths from a point A to itself. So here's one possible path from A to itself. There it is. And you might have some other one, like this. Who knows? And maybe these are up to homotopy the same path. Why? Why would that be? Well, that would be because we can find a big F, a continuous deformation of one of these paths to the other. So you can imagine that there's a sequence of intermediary paths, a continuous map, big F, which takes one of these paths to the other one. Now it turns out that if you have the same, if A is equal to B here in this case, right? We call this point, let's give it a name. Let's call it X. Not A, let's call it X. Okay? Then it turns out that this, the set of homotopy classes of paths from X to itself forms a group. A group. And it's called pi 1 of big X, small x. It's called the fundamental group. So it's pretty big deal. It's a pretty big deal. Now maybe you're asking yourself, well, aren't all paths equivalent under this relation? No, they aren't. So, for example, what if you had a hole in your space? You see that? That's a hole in the space. So we don't know what it means to sort of go past this point here, or to map into this point here. We don't know what it means. So in particular, these paths, although these paths are still the same up to homotopy, this path right here, okay, this path right here is homotopically distinct from these other paths. This represents, in fact, the trivial element in this in pi 1, whereas this thing here represents something non-trivial in pi 1. It's all very important. It's all very interesting. It's all quite lovely. And that's the beginnings of homotopy theory, which is goddamn miles deep, okay? It seems like homology is just like homotopy with a bit less information. Homotopy is pretty serious, right? Think about, for example, is it Whitehead's theorem? I never know what to attribute to Whitehead. What is it? So there's a theorem that says basically if you know all the homotopy groups, you know the space up to homotopy. It's pretty baller. Like, I think maybe it's restricted to CW complexes or something like that. But homotopy groups in general are quite strong. Yeah. They're a strong ass invariant. If I take a punctured plane, does pi 1 have only 2 elements? So a once punctured plane? A once punctured plane, well, it has infinitely many elements. A once punctured plane, so like this guy, if we think about the plane minus this hole, pi 1 of x, it turns out to be equal to z. The free group on one generator is the way you should think of that. If you had 2 holes in the plane, you know what you get? Z star is the free group on two generators. Z star Z is one way to denote it. And with 3 holes, Z star is Z star is Z. Did somebody... I'm not paying attention. Oh, yeah. Hey. Hanging chat. It's just hangingchat.com, right? How come Puzzle Gamer doesn't hang out anymore? I miss them. Yeah, Skugget's got it. Anywho, so Linux, where are you at? That's right. So you could go around this thing twice, okay? Continuously. That's a single, we consider that topologically like a loop, right? It satisfies the condition, but it's not the same as going around this thing once. Oh my god. Okay, so let's see. What is the right way of doing this problem? Still continuous, right? So, yeah, let me write it down first. The absolute value of x minus 2 over 2x plus 1 is less than or equal to 1/2. We want to solve this monstrosity. Now, the way that I'm going to attack this one, all right. I think the way I want to attack this one is to first subtract 1/2 from both sides. This is a very similar problem, but slightly different in a way that maybe makes it easier to talk about. So let's do this. Zero is nice because then I can talk about things being positive or negative, right? So I'm going to do this at first just to make it so that the discussion is easier to talk about. Remember how much trouble I was having discussing it before? I think having the words positive and negative in my pocket available to use here is valuable. So that's why I'm going to do this first move here. It's not strictly speaking necessary, but I'm going to do it. Okay? Now, what we want to do is to think about what are the possible locations, possible values of x, which could possibly make this expression here change sign. And what do I mean? I mean go from positive to negative or from negative to positive. That's the question that we want to concern ourselves with. So there's two types of places where this expression could possibly change sign. The reason why there are only two types is because this expression here is continuous on its domain. What I mean is that, with the exception of places where this function is not defined, you can draw the graph of this thing without lifting up your pen. The points where this thing is discontinuous are problematic. We need to keep track of those. Where is this thing here discontinuous? There's only one point, by the way, where it's discontinuous. And where is it? You tell me, please. Sorry, yeah, I spaced out. At x equal to negative 1/2. That's exactly right, when this thing here is 0. So we want to keep track of x equal to negative 1/2. What I'm going to do is I'm going to draw a real line here. And I'm going to put x equal to negative 1/2. The reason I'm drawing this now is because I'm preparing to cut this real line into pieces. And then pick test points, just like we did before. All right. So there's one of the cut points is at x equal to negative 1/2. Let's see if we can find any others. What are some other places where this quantity here could possibly change sign? The other type of place where that could happen is places where this quantity is equal to 0. Right? Where the graph of this goes, where it crosses the x-axis. Those are places where it could possibly happen that this changes sign. Do you agree? So we should figure out when this quantity here is 0. I have no idea. But I think that what we're going to need to do is to break this up into cases, unfortunately. And the reason is because of these annoying absolute value bars. Incredibly annoying, right? So we break this up into cases. I think. Is there any, I think that's the best thing to do. Ooh, no, let's not do that. That seems really gross. Does it? What we could do is, yeah, move 1/2 to the other side and then square both sides. I'm not sure if we want to do that to ourselves, though. You want to do that to ourselves? It's only 2x minus 1/2, right? Or is it? Oh, is it plus 3/2? And I have to square 3/2. Oh no. No, that's not happening. And now I have to do twice as much work. Okay, this is what happens to me when I'm doing. We just push forward. Okay, just go. Let's just go. We're gonna break this up into cases. The first case. Break into cases. The first case is when x is greater than 2. Or greater than or equal to 2. So what is true if x is greater than or equal to 2? Well, the absolute value, well, so what's true is that x minus 2 is non-negative, right? So the absolute value of x minus 2 is x minus 2. Does that make sense so far, Linux? Hi. So now we have x minus 2 over 2x plus 1 is equal to 1/2. And we can solve this equation. So I've moved 1/2 over to the other side. This is now, I hope, a standard solve for you. If not, we're going to go through it right now. What's my first play? Multiply both sides by 2x plus 1. Right? You have to be a little careful here because if x is equal to negative 1/2, oh, wait, never mind. X is not equal to negative 1/2. We don't have to worry about that. Never mind. I'm not even sure why we had to worry about it anyway. So then what? Then we get x minus 2 is equal to, now I'm going to distribute the 1/2 in, x plus 1/2. And hopefully you're getting a little hot under the collar. What the fuck is this? How can a number minus 2 be equal to some number plus 1/2? And we can make this really stark if we subtract x from both sides, right? We get to learn that negative 2 is equal to 1/2. But you know, as well as I know, that negative 2 is not equal to 1/2. What does that mean? That means that there are no solutions. There are no solutions to this equation when x is greater than or equal to 2. Characteristic 5. Is that true? Okay. Okay. Great. No solutions. All right. That's good. I don't know if it's good or bad. That's just the way it is. What's that song? That's just the way it is. Who sings that song? That's just the way it is. Things will never be the same. That's just the way it is. Roger Hornsby? Dan Hornsby? I don't know. Case 2. Well, it's the opposite case. It's when x is less than 1. No, I mean less than 2. Oh yeah, it's a Tupac song too, right? Yeah. But no. That was originally a song by some white guy. I don't know what the white guy's name is though. I don't remember. Sorry. So if x is less than 2, what's special? The absolute value of x minus 2 is now equal to not x minus 2 anymore, but rather negative x minus 2. Do you like it? Do you accept it? I find a lot of students freak out about this. So if you're freaking out, that's okay, but you have to let me know, because you need to be able to do this on your own. So if x is less than 2, then x minus 2 is negative. Bruce Hornsby. Got it. Thank you, Weird Alex guy. So the absolute value of x minus 2 is negative x minus 2. Do you like it, Linux? You don't understand why. Okay, good. So just real quick, just in thinking about it. What's the absolute value of negative 2? I know you know what it is, but just say it out loud, okay? It's 2. And you know what 2 is? It's negative negative 2. What the absolute value bars do to the thing inside when the thing inside is negative is it applies another negative sign to it. So if x is less than 2, x minus 2 is negative. What do the absolute value bars do to that then? It applies another negative sign. Tell me if that feels good or bad. It makes sense. Yeah. Good. If you carry that little gem with you, that rock around with you, that boulder, if you let that sit inside of your brain, don't look at it too much. No. You should fully take it on board. You'll have an advantage because a lot of kids are confused. I don't know why I'm crossing this out. This is like involuntarily happening. Okay, I don't understand why that happened. Anyway, so we have this now. Remember what we're trying to do. We're trying to solve this equation here. If we're solving for all the regions where this function is less than or equal to 1/2, we've shown that when x is greater than or equal to 2, it's not equal to 1/2. but it's still always less than 1/2. What? No. I'm sorry. What we're trying to do right now is, apart from this question, we're answering this question. When is the absolute value of x minus 2 over 2x plus 1 minus 1/2, when is that 0? We found that in the first case where x is greater than or equal to 2, we had no solutions. In the second case, we need to solve. So what we have is negative x minus 2 over 2x plus 1 is equal to 1/2. We multiply both sides by 2x plus 1. We distribute the negative 1. Over here we get x plus 1/2. We add x to both sides. We subtract 1/2. Tell me if I'm going too fast. And then we divide both sides by 2. Did I do my math correctly? No idea. Oh, good, Skugget. So, notice that there was a bit of a lie here. Good. There was a bit of a lie because when I multiply both sides of this equation by 2x plus 1, if x was negative 1/2, then I would be multiplying both sides of this equation by 0, right? And so we destroy the information in this equation when we do that. Multiplying by 0 is the most violent thing that you can do to an equation. There are some other violent things that you can do, but by far the violentest, the most violent thing you can do to an equation is multiply both sides by 0. So we need to be careful, and we need to consider that situation very carefully. If we, but please notice that x equal to x equal to negative 1/2 does not arise as a potential solution to this equation. All we get is x equal to 3/4. So if we want to be absolutely proper, then what we have to say is that this equation is equivalent to this equation as long as we make the proviso that x is not equal to negative 1/2. Right? These are exactly. That's why it's the violentest thing you can do. Anyway, look at the solution that we did obtain, though. X equal to 3/4. Should we put it on our real number line or what? What do you think? Is this a possible place where the sign changes? Yeah, it is. And the reason you want to make sure, just to make sure, is because this 3/4 is less than 2, right? So, good. So 3/4, maybe it's right there. All right? So I claim that these are the possible places, not definitive places, but possible places where this expression here could change sign, this expression. So now we're going to play the game of test points. So you choose. What's a good test point over here? We're going to cut up the real line along these two places. We're going to pick test points inside each. What test point do you like there? I'm reading your mind. I know you like -1. how about inside here? What test point do you like between negative 1/2 and 3/4? Again, I'm reading your mind. I already know you like 0. Okay. And something over here on this interval, I already know what you like there. 1. Okay. So now we have to do arithmetic. So test point sine of absolute value x minus 2 over 2x plus 1 minus 1/2. And this is the hardest part, arithmetic. All right. Negative 1 minus 2 is negative 3. That's a great point. We're going to choose 2 because learning balance is smart. We're going to put in negative 1 into here. What do we get? Negative 3, right? But we're taking the absolute value of it. So it's 3. We get 3 upstairs divided by negative 1. So the whole thing here is negative 3 minus 1/2. I think we can agree this is negative. Can we agree? Please confirm or deny. I am not to be trusted here. This is... Are we happy with this? Oh, okay. How about x equals 0? So we get negative 2 up there with the absolute value bar. So it's 2 divided by 1. That's 2. Minus 1/2 is 3. I don't know what it is. It's positive, though. Learning balance. Time wizarded right there. And notice that at x equal 2, we get the beautiful 0 upstairs. We get a gorgeous 0. Ah. And then 0 minus 1/2 is negative. Okay. So this expression is negative, or rather it's only positive for, on this interval. And it's negative elsewhere. Oh, actually, but we need to know that. We're interested in that. Okay? Now, the only other possible things that we need to know about are negative 1/2 and 3/4. What do we know about 3/4? How did 3/4 come about again? Because that was a place where this expression was equal to 1/2 on the nose, or rather where this thing was equal to 0 on the nose. So we want to include 3/4, but of course exclude negative 1/2. Oh, I should put a big old white bubble there. Hollow bubble. There. So what is the solution then in the end? Where is this inequality satisfied? It's satisfied for x in the interval from 3/4 to positive infinity, which we denote like that, but also for x less than negative 1/2. So we might write union. That's a u without a tail. It's called union. It's a u without a tail. You don't put a tail. Don't do that. Union negative infinity to negative 1/2. And we look at the roundy bracket on the negative 1/2, okay? That indicates that we are excluding negative 1/2. I'm pretty sure this is right. The way then we check to see that we did our algebra correctly is we look at desmos.com. That's not command. Is it abs? Okay, so here's that goofy function. And what we are interested in is when this is negative. And we said it's negative from 3/4 onward. Does that look like 3/4? Hell yeah, look at that. And it keeps going. It's just beneath the x-axis there. And it's also negative to the left of -1/2. So -1/2 is right here. X equals -1/2. We see it being negative all the way over there. We did it! Also plot x equals -1/2 for clarity. Yes, sir. There we go. So this is a vertical asymptote again. Yeah. And look at this little kinky little thing that happens there at 2. This is such a good site. All right, cool. I hope that you understood all that. You're very welcome. Thank you for the good questions. Weird Alex guy. If you've got a math question, type !join to join the queue. So right now, the queue is empty. I mean, you'd come right after Weird Alex guy. Do I do differential equations? Not well, but you know, I do my best. If it's anything like beyond the intro class, then almost certainly I'm not going to be able to do anything with it. I'm sorry to say. That's nice of you to say, Linux. I wish I had you as my student. You seem to be really on top of it. I mean that. So you have a linear differential equation set equal to some function. How do we select a fitting function? So do you just when you say fitting function, you just mean like a possible solution or a form for the solution? And in particular, are you talking about this method of undetermined coefficients thing? It's a little unclear to me, but that's just because I don't know what I'm talking about exactly. Like I don't I don't know the words, the jargon. I'm sure, or I'm not sure, but I would guess that there's a lot of jargon in the field that I just am not aware of. So it might not be your fault at all. It might be just my own ignorance, which I'm happy to admit. Yeah, Linux. University is serious. And high school, I wouldn't say it's a joke exactly, but it's serious in university. I have a feeling that what he's asking is the method is for the method of undetermined coefficients. Do you know what? Do other people know what I'm talking about when I say that? Where you sort of, based upon the form of g of x, you make a guess at the form of a solution. of a particular solution. So like let's just look at a quick example. So like let's say that you had a differential equation like y double prime plus 3y prime. I don't want to make this hard on myself. Plus 2y equals e to the t. What's a good choice? What? No, this is not good. I have no idea what I'm doing. Okay, we're just gonna go with this though. I think this is working great. Okay, I'm super confident. Okay, super confident of what I've done here. Let's say you've got this guy. You're looking at e to the t. You're trying to guess any particular solution, right? Because if you find just one particular solution, you know the entire thing because you know how to solve the homogeneous equation super easily. Do you know what I'm talking about? Weird Alex guy? So you just want to make a guess. You just want to guess. Just guess what the solution will be. Here's my guess. Oh, wait. Wait, what am I doing? Maybe this isn't going to end well. Let's see. Let's solve the complementary solution first. First, let's find the solution to the homogeneous equation. So what we're going to do is do y double prime plus 3y prime plus 2y equals a big fat 0. Huh? So this is where you do the characteristic polynomial thinger. Oh no, this is fine. I don't know why I'm worried. I don't know why I got worried. But so we're going to take the characteristic polynomial, which is super easy to write down, right? It's r squared plus 3r plus 2 equals, and what we want to do is find the roots. Oh no, this is bad. Wait. Fuck. Holy shit. Okay, this is actually bad. Never mind. This is bad. So, no, it's good. I forgot. It's good. I think it's good. I'm struggling, okay? Here we go. I think it factors like that, right? It's good. It's good. This is great. So the complementary solution, y sub c, this is great, is c1 times e to the negative 2t plus c2 e to the negative t, right? This is great. Good. Very good. This is great. Now, so now we're going to try to find any particular solution that we can. Because if we can find any particular solution, y sub p, we can add y sub c to y sub p, and that will represent the full set of solutions to this equation. Now, to do that, we use this thing called the method of undetermined coefficients. And we make a guess about the form of the solution to this non-homogeneous equation based upon the form of this guy. I don't know what you call that. This guy. this guy, based on the g of t. Oh, you call it g of x, but I'm using the independent variable t. So adapt. So here's my guess to find y sub p, the particular solution. Guess y sub p is exponential, yeah. And in fact, a equals e to the t. It does help. I know what you're talking about because this is like a harmonic oscillator, and this is the external force acting on the harmonic oscillator. But not everybody uses that terminology. Well, almost. Okay, so we have to be smart about it. But like with commonly used functions, like there's like a table. There's like a table, okay? And we like tables. No, do we? I'm not sure how we feel about tables. But let me pull it up. Like, I'm pretty sure if I do method of undetermined coefficients, there's guidance out there, in other words. A table. That if g of t has these particular forms, these are the guesses that you should make about the form of the particular solution. Look, they're even using our same letters, the same letters. They use G2, they use T, and Y sub P. Everything's the same. Anyway, the point is that what you do is you put coefficients everywhere. You make the form, you make the guess based upon the form of G of T. Now, there is one important thing to say about this. So, if you plug in this y sub p into this expression, what you're going to end up with, I guess, is a quadratic in A, and then you do some work, and then you win to figure out what A is. Because this will be a solution to this guy for some value of A. I have no idea what it is. I'm sure you can find it. Is that clear, Weird Al X? But I do want to say, what if the problem was a little different? What if we had instead y double prime plus 3y prime plus 2y equals, let's say, e to the negative t. So what is the difference? The g of t is slightly different, right? What if this was the equation that was in front of our face? Then if we were to use this method of undetermined coefficients naively, we might guess that the solution looks like y sub p equals a e to the negative t, right? We might guess that. But what I want you to observe is that this y sub p cannot possibly work. This cannot possibly work. It's failed from the very start. And the reason is because look at the complementary solution. And please notice that this particular choice of y sub p is already inside the complementary solution. Set C1 equal to 0 and C2 equal to A. So this cannot possibly work. Y sub p is subsumed, is contained in the complementary solution. So the solution in this case is to instead guess a t e to the negative t. Just put a t on it. Tack a t in front. And try that. So you have to do some work here. You have to do some product rule. It's gross. Yeah. But it should work out. Yeah. It's very ad hoc. It's very like, I don't know. Oh, so rather, my limited understanding of the theory of differential equations, which is limited, suggests to me, it looks to me from my vantage point to be a very ad hoc kind of method for finding particular solutions. There are, of course, other ways of doing these kinds of problems. Like there's, what's that thing called? The Laplace transforms, which feel much more powerful to me. Not ad hoc. They feel good. So that's coming in your future. Yeah, go ahead, Ariana's Gari. What is your question? Let me bring it up. Assume that y equal to y of x is an implicitly defined function satisfying that equation. Find y prime and y prime. Find y prime and y double prime. Oh. Okay. I don't know. All right. What do we do from here? Stream music mutes my audio in VODs. That's the problem. I'm sure there's some public domain recordings somewhere that I can use. How do I get started on this, Ariana's Gari? We don't need to subtract 6, no. Because remember what we're after. We're after y prime. And y double prime. But that comes later. What can we do to this to get at y prime? To see a y prime appearing in our midst? Monkso, thanks for following. I don't know is a legitimate answer. No, so here's what I think you should do. What you should do is take d dx of both sides. God. I'm sorry. d dx of both sides. So what we're going to do is take d dx of... Yeah. I think, you know why he's crying, I think? Because his mom won't open her new iPhone before he gets his work done. All right, so anyway, d dx of x squared plus 2y squared is equal to d dx of 6. All right, first question, the easy question. What's d dx of 6? Yep. Harder, but still pretty goddamn easy. What's d dx of x squared? Remember, ddx is a linear operator. I don't know if you know what that means. ddx respects sum. So ddx of x squared plus 2y squared is equal to ddx of x squared plus ddx of 2y squared. ddx of x squared is, just as you say, 2x. Good. And now what is ddx of 2y squared? This is legit tricky. What is ddx of 2y squared? Oh, great. You know it. Yeah, exactly right. And this is because of the chain rule. 4y, y prime. Good. So now what you can do is solve for y prime if you want to. And you do, because that's what you're trying to figure out, right? Y prime is equal to negative 4y over 2x. That's okay. Is this making sense, though? Which is negative 2y over x. This is y. I don't. Oh, should it? I don't know. You don't. And of course, what we do from here is subtract 2x from both sides and then divide by 4y. So we can solve for y prime, in other words, and we get that this is equal to, of course, negative 2x over 4y. What else could it be, right? And of course, simplifying this gives you the final answer that you would like to give to your instructor, negative x over 2y. You box this, move on with your day. This is very confusing. Yeah, I'm not sure what happened there, but just want to make sure. Okay, there we go. Looks better. Great. Any other questions out there? Any other questions for anybody? From anybody about anything? Oh, I'm sorry. We've all been there. All right. Well, we did it. Good job. I need a new piece of paper because, in fact, let's just put all these. Let's just put these over here. Am I a lax parent like my mother was? I'm actually no. I'm actually a little bit more hardcore than my mom was. But like, I like to think that I give my children lots of opportunities. I push them to look at lots of things. So like, I kind of poor boy. One sec. Hold on. But no, I'm not as lax as my mom was. No. But like if I don't know. I don't think I'm a tiger parent either. I don't think I'm falling into any of the usual stereotypes about like I care about my kids having good lives, like a functional, adulthoods and such. Absolutely. On the other hand, not particularly interested or care about whether they become a doctor or a lawyer or anything like that, or make like buku dollars or something like that. Don't care about that. I'm more interested that they become happy, functional individuals. I'm learning about matrix. Is there any reason to solve systems of equations in matrix form? So you could conceivably, I would imagine, do all of linear algebra using systems of equations, right? You just write, whenever you write a matrix, you write a system of equations. I think that, or a system of expressions, let's say. You could conceivably do that. But it would be absolutely horrific. And to such a degree that no, it would just be absolutely horrifying. Absolutely horrifying. You don't want to do it. You really do want the matrix there because it makes things way more conceptually accessible. Okay. So there is a reason. Save the ink. Save your ink. Have I seen Axler's textbook about linear algebra? I actually haven't really ever looked at it carefully, but I hear a lot about it. 2 months behind on pre-calc. Doing a bunch of shit right now. They're not bad, but it's kind of a lot. Do I have a good understanding of Hilbert's Nullstellensatz? I know what it says, but I would not say I have a good understanding of it. I know it, like, I think I know the weak or something. The weak version? I can't remember which one I know. I know something, but which is vaguely called a Nullstellensatz, but I'm not sure what it really is. So here's my idea of what the Nullstellensatz is. So there is a correspondence between algebraic sets and ideals of certain polynomial rings. I'm sure I'm not saying the right words. There's probably the word affine somewhere, but I don't know what the fuck all that shit is. All right. So, for example, if you think about just the point 0 in C, one-dimensional C, that is to say, complex plane, just think about the point 0. Then you can think about the set of algebraic functions on that variety as being C bracket X modulo the ideal generated by X. So every one of the functions in this ideal here vanishes at 0 of C. And so we can suitably regard this as sort of the ring that we might associate to 0. On the other hand, we could also think about C bracket X modulo the ideal generated by x squared. Now, it's still true that every function in this ideal vanishes at 0, right? Every function in this ideal vanishes at 0. But somehow it's it still leaves something to be desired if we're going to be thinking about a strict correspondence between algebraic sets with no further information or decoration and ideals. So what the Nullstellensatz says is that your hope is not lost. What you can do is instead think about for the radical of an ideal. So you can think about radical ideals. So basically every algebraic set has associated to it a unique ideal, a radical ideal, where this kind of redundancy basically does not arise. I think that there are certainly contexts in which you might want to think about, for example, this ideal, right? Because certainly there's something different about the set of functions that look like x squared times something versus the set of functions which look like x times something. Like somehow a derivative of this guy, of the functions in here, are also all 0. So there's additional sort of geometric information contained in here. But I think what the Nullstellensatz is sort of saying is that if all you care about is, let's say, just the algebraic set, then you look at the radical of the ideal. So the radical of this ideal would be this ideal. And then you set up a one-to-one correspondence between algebraic sets and ideals. I don't know if that made any sense at all. That's the best I can do. If I was to talk to an algebraic newbie, what words of advice would I give them? What is the context here? When we say algebraic newbie, are we talking about a 10-year-old? Or are we talking about like a math major? What are we talking about? No, I mean, like, are they studying algebra, like how to solve 3x plus 5 equals 8? Or are they studying algebra like the first isomorphism theorem first isomorphism theorem? Is that what it's called? For groups? Whomst are we talking about here? Are we talking about abstract algebra here, or are we talking about like algebra 1 in high school or middle school? Algebra is it's quite multifaceted. I don't think it's like a linear track. Like algebra in high school, or before you get into like what abstract algebra is, most people's understanding of what algebra is that it's sort of about solving equations, manipulating equations so that ultimately they can be solved, right? So like manipulating that guy so you can figure out the value of x. I think that's algebra. I do think that's algebra. But that is quite different in character than issues in algebra when you are a math major starting out in your abstract algebra class. I don't think the final goal is to be able to get better at solving equations, for example. Now, obviously, there's stuff like Galois theory, but that is just one facet of issues in algebra that have now been sort of placed under the umbrella of algebra. So the first thing that I'd want to know if I was talking to an algebraic newbie, as you put it, is who that person is and what they're studying. I never took it. I never took Galois theory. In fact, I'm pretty ignorant of it. It feels strange. But it never came up in my abstract algebra sequence or in any of my algebra courses. Yeah, I do. But there are definitely other things that interest me too. It is. I just never got around to it, I guess. I've always been somewhat intrigued by the analogy between field extensions and covering spaces, though. Calculus and linear algebra together. I'm sort of, I think, very much in the mainstream in this with this take. They really do form two pillars for a lot of applied uses of mathematics. So linear algebra is incredibly important. Differential equations, yeah, they're important, but linear algebra and basic knowledge of calculus, I think, are incredibly important. It really depends on where you're going, right? What's the word in English for an equation that you use to solve initial value problems or to find the common answer? Oh, we call that the characteristic polynomial. I don't know why it's called that exactly. Because that phrase is also used in the context of linear algebra. Oh my God. That we'll have to have a little bit of a reading time. We'll read out of that manga a little bit later, okay? I'm invested. Are they going to get together? That guy and girl? That's really what's motivating me to read. Yeah, the linear algebra manga. The manga guide to linear algebra, I believe is what it's called. Vienna linked it to us yesterday. Oh, you can convert an ODE into a matrix equation. Oh, okay. This is the link. If nobody has any questions, we can take a look. Now, here it is. This is where we left off. But hey, please interrupt me, okay? Because this is a little bit weird for me. Oh, you did? Where? I didn't see it. Would you argue that calculus, linear algebra, and how to write proofs are the tools for higher math? You know, I think calculus and linear algebra are both sort of no, I left it open all night, Vector. I think you can go into a lot of courses, math courses, Vienna, without strictly speaking calculus and linear algebra. But at some point you're going to get blocked. At some point you're going to hit an obstacle. Oh, it's absolutely indispensable for engineers, yeah. For physics as well. You need both. It's pretty important for mathematicians as well if you want to stay sort of in the mainstream. Like, you can go off and study something insane, like magmas or something like that, and probably never run into any linear algebra or calculus. But, like, if you stay on a sort of a standard track, I'm not sure if that's the right word, but if you you will run into it. You will run into linear algebra and calculus. What are the important precursors for differential geometry? Linear algebra and calculus. But also, you probably want some, maybe a bit of topology, enough to understand what a manifold is, for example. You definitely need lots of linear algebra. Calculus couldn't hurt. In fact, it would be really good for you. Okay, yeah, so engineers might not take a linear algebra class. I've seen this. Okay, I have personal experience with it. However, you definitely get it, because you can't do differential equations, like systems of differential equations. You can't do that without linear algebra, for example. So you definitely see some linear algebra. You might not see it done right, but you definitely get some of it. Do I stream every day? I do. I got a good book for common sharks? I don't. Learning linear algebra might actually be damaging for magma theory. Yeah, maybe. Get your mind. You have to get your mind. You have to do something to your brain to really get. Well, whatever. Excuse me. I'm starting a master's dissertation at the moment, and it's basically on extending calculus and a bit of linear algebra. Cool. How does that work? See? Hey. You know what we should do? More of? Some of? At all of? Any bit at all of? We should have you smart folk that are smart. Okay? Get on Discord and talk at us about the things that you're passionate about, because I want to hear it. And you have to do it in a way that's suitable for, like, you have to target it at an audience like the people in the chat, for example, that we can understand, so that we can learn from each other. And you know what? It'll make you stronger in the process. You should do it. You all should do it. Wait, let's read this manga. Oh, also, manifolds use something to combine two or more fluid streams. I don't know. I don't know anything about fluids. I know nothing about fluids, okay? Going on record. I know nothing about fluids. So don't try. Never mind. You're ready to discuss Stirnerian anarcho-individualism at my command. There's a book from a couple of years ago developing some theory on a sort of calculus on square matrices of arbitrary size. Currently, we're working through that. Is water a fluid? No comment. Linux. Gex. Sweet dreams, buddy. Thank you for the questions. Hope to see you again. All right, manga time. So even if I decide to study it, it won't do me any good in the end? She asked. Look, she's nervous. I think that's what that little thing there means. Does this... I've never read a manga in my life. I am ethnically Japanese. This format for comics or of graphic storytelling, it means she's nervous. Yeah. Okay, she's nervous. That's not what I meant at all. For example, for an aspiring chef to excel at his job, not sure about this, he has to know how to fillet a fish. It's just considered common knowledge. The same relationship holds for math and science students in linear algebra. We should all know how to do it. I see. Like it or not, it's just one of those things you've got to know. Best not to fight it. Just buckle down and study. You'll do fine. I'll try. There's also a lot of academic literature that you won't understand if you don't know linear algebra. Isn't this one read from left to right? I have no idea. Is that how this shit works? No, I'm supposed to read from like normal languages. Regarding our future lessons. I'm just reading now. Regarding our future lessons, I think it would be best if we concentrated on understanding linear algebra as a whole. Look at this. I like this image of looking out upon a landscape. I think this is a powerful idea for mathematics. Okay? There is a landscape out there, all right, that you are exploring. I like it. Most books and courses in the subject deal with long calculations and detailed proofs. I'll try to avoid that as much as possible. Woo! And then look at this nerd. Look at this guy. We can't even see his face. He's a robot. Not human. There's something inhuman about this person and what they are doing. And focus on explaining the basics as best I can. Great. She's so happy. And there are beads of sweat coming off of them. What? They just seem happy. Well, I don't want to overwhelm you. Why don't we call it a day? They've hardly done anything. We'll start with some fundamental... Sorry. I know how to read, okay? Just take it easy. We'll start with some of the fundamentals next time we meet. Okay. Ring, 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 ring. Oops, that's me. How embarrassing. It's from my brother. Oh? The sensei texts? Hard to imagine. Oh, so some setup for those that didn't see yesterday's episode. Her brother is the sensei at a, I guess, martial arts dojo, of which this guy, whose name I can't remember, is a student. Sensei asked this guy to tutor his little sister in linear algebra because she was having trouble with the course. And this dude is, a nerd and he knows it. But now he was, at first he was feeling a lot of trepidation because, you don't know who your student is going to be. He had no idea what this girl would be like. But then he discovered, oh my God, she's this cute girl. And so then he started getting real thirsty. And that's where we're at right now. They touched hands though. That happened. Their hands touched at a certain moment. And he nearly... Yeah, I was about to get really lewd. Never mind then. The Fundamentals, Chapter 2. Okay, sorry. 97, 98, 99. You've got to know your basics. Whoomp. 100. Done. You wish, after you're done with the push-ups, I want you to start on your legs. That means squats. Go, go, go. Look at how the text is like, I can highlight it. It's amazing. Hey, I guess this is later. Hey, I thought we'd start off with Raiji, you seem pretty out of it today. Are you okay? I'll be fine. Take a look at this. Rumble. Wait, how can I do sound effects? Does this sound like a rumble? Does that sound like a rumble? I have no idea. Oh, that's a stomach. How embarrassing. Sorry, I guess I could use a snack. I can't believe we did this. She's not impressed. She can't be impressed. A man that cannot organize his day enough to prevent his stomach from growling? What kind of man is that? No kind of man for her. Am I right? Don't worry. Pushing your body that hard has its consequences. Oh, I guess she was aware of the hard training that he was doing a little bit earlier with her brother. Just give me 5 minutes. I don't mind. Take your time. Nom, nom. I'm not going to do that one out loud. Well then, let's begin. Take a look at this. I think that's the appropriate voice for this guy. A cracking voice. Oh shit. Is this going to be not safe for work? I just assumed that because this was linked on math.ucla.edu that this wouldn't go straight pornographic on me. But maybe I should be a little careful. I'm trusting for now, okay? I took the diagram of what I took the liberty of making a diagram of what we're going to be talking about. Wow. Course layout. Fundamentals into matrices and vectors into linear transformations and eigenvalues and eigenvectors. Recall, please. These were the mountains out there in the terrain that is linear algebra. These are the mountains, the twin mountains they will be ascending. Hopefully, over the course of the manga. Of course, there's another mountain left unspoken. You know what I'm talking about. Love. That's what I'm talking about. Love. What were you thinking? Mountain of love. They're slowly climbing it together, hand in hand. Will they make it? I don't know. There's plenty of dangers along the way. I thought today we'd all start on the basic mathematics needed to understand linear algebra. We'll start off slow. We'll start off slow and build our way up to the more abstract parts, okay? Don't worry, you'll be fine. Sure. Oh, complex numbers. Complex numbers are written in the form a plus bi, where a and b are real numbers and I is the imaginary unit, defined as I equals the square root of -1. Not sure if I should get mad or not. Real numbers, integers, positive natural numbers, 0, and the negative natural numbers. Rational numbers, not integers. Terminating decimal numbers like 0.3. Wait, 0.3 doesn't terminate. Does that mean terminate? Is it appropriate to say these terminate? Non-terminating. Oh, I'm sorry. You didn't hear any of that. Non-terminating decimal numbers like 0.3. Yeah. Okay, great. Numbers like pi and square root 2 whose decimals do not follow a pattern and repeat forever, right? Imaginary numbers. Complex numbers without a real component, like 0 plus bi, where b is a non-zero real number. Numbers that can be expressed in the form q over p, where q and p are integers and p is not 0, are known as rational numbers. Integers are just special cases of rational numbers. Let's talk about number systems first. They're organized like this. Not sure how to vocalize that. Complex numbers, I've never really understood the meaning of I. Well, I don't know for sure, but I suppose some mathematician made it up because he wanted to solve equations like x squared plus 5 equals 0. So, x squared plus 5 equals x squared minus negative 5, which is equal to x plus square root of 5 plus times x minus square root of 5 whatever, I missed some i's, equals 0. Using this new symbol, these previously unsolvable problems can suddenly become approachable. I know, look at her, she's bored. I don't know, she might look a little thoughtful here, I'm not sure. Trying to make sense of it. Why would you want to solve them in the first place? I don't really see the point. I understand where you're coming from, but complex numbers appear pretty frequently in a variety of areas. Sigh. I'll just have to get used to them, I suppose. I'll just have to get used to them, I suppose. Don't worry. I think it'd be better if we avoided them for now, since they might make it harder to understand the really important parts. Thanks. What's happening here? Oh, wow. Implication and equivalence. Propositions. I thought we'd talk about implication next. But first, let's discuss propositions. A proposition is a declarative sentence that is either true or false, like 1 plus 1 equals 2, or Japan's population does not exceed 100 people. That is either true or false. Nervous here? Let's look at a few examples. A sentence like Raiji Yurino is a proposition. Raiji Yurino is sorry, did I say that right? Raiji Yurino is male is a proposition. Raiji Yurino is female is also a proposition. By the way. True. Wait, what? True. But a sentence like Raiji Yurino is handsome is not. My mom says I'm the most handsome guy in school. To put it simply, ambiguous sentences that produce different reactions depending on whom you ask are not propositions. That kind of makes sense. Hey, if anybody's got any questions about anything, math-wise, just ask, okay? We're doing story time right now, but I will interrupt story time in an instant to help you. Hi, CootieJuice69. How are you today? What am I doing? is the continuum hypothesis a proposition? Seems that way. Is it a proposition? It's either true or false, right? I'm sorry, Cootie Juice. Sorry. 69. Cootie Juice 69. Implication. Let's try to apply this knowledge to understand the concept of implication. The statement, if this dish is a schnitzel, wow, then it contains pork, is always true. Wait a minute. I don't know very much about things. Okay. However, is there not such a thing as chicken schnitzel? This is a thing. Porkless schnitzel is a thing. Chicken schnitzel. So this statement is always true. I beg to differ. I keep doing Haiji. I'm not sure why. What should it sound like more? This is my own ethnicity too. So it's a little embarrassing. Raiji. Raiji. I think that's better. Raiji. But if we look at its converse, if this dish contains pork, then it is a schnitzel. It is no longer necessarily true. Raiji. Hey, I don't know if I've told you this story before. In fact, I know I have told you this about 500,000 times. So I'm lying. But here's my story. When I was a small child, I was walking along a grassy hillside, and down over here was the playground, and here's my epiphanic moment that I want to share with you right now. I realized that if I had in front of me a square, if there was a square in front of my face, then you know what was also in front of my face? A rectangle was in front of my face. However, if I had a rectangle in front of my face, it was not necessarily a square. Very important moment in my life. Moving on. Why is he so mad? Oh, pig's feet. Pig's feet. In situations where we know that if P then Q is true, but don't know anything about its converse, if Q then P, we could say P entails Q, and that Q could entail P. It is a schnitzel entails it contains pork. It contains pork could entail it is a schnitzel. I'm weirded out by this whole discussion, actually, of entailment. But, okay. When a proposition, like if P then Q is true, it is common to write it with the implication symbol, like this, like that. I think I get it. Oh, she's happy. Equivalence. If both if P then Q and if Q then P are true, that is, P implies Q as well as Q implies P, then P and Q are equivalent. So it's like the implication symbols point in both directions at the same time? Exactly. It's kind of like this. Raiji is shorter than Tetsuo. Tetsuo is taller than Raiji. Don't worry, you're due for a growth spurt. You know what Wiener Schnitzel is in the United States, right? It's a fast food restaurant that's absolute trash. Well, I don't know, actually. I don't really know. I can't really say that. But like um the architecture is very unique because it's like a mountain villa with very high steep roofs, roofs, but it's in the middle of, like, you know, often in between a pair of liquor stores, dumpster out front, that sort of thing. That's Wiener Schnitzel in the United States. And this is the symbol for equivalence. Raiji is shorter than Tetsuo. Tetsuo is taller than Raiji. All right! She's hype. Set theory. Another important field of mathematics is set theory. Oh yeah, I think we covered that in high school. Probably, but let's review it anyway. Her appearance has changed. Feels weird. Just as you might think, a set is a collection of things. Oh, really? Have they consulted NCAT about this? The things that make up the set are called its elements or objects. Hee hee, okay. Why is this funny? Wait, why is this funny? Is it because he's making this dumb face? Is that what she's laughing at? This is not going well for him. This might give you a good idea of what I mean. The set Shikoku, which is the smallest of Japan's 4 islands, consists of these 4 elements: Kagawa-ken, Ehime-ken, Kuchi-ken, Tokushima-ken. I don't like this because this is like somehow this God-given or something. Like, if I say Shikoku, you should know these are the 4 elements. This is bothering me. The set consisting of all even integers from 1 to 10 contains these 5 elements: 2, 4, 6, 8, 10. A Japanese ken is kind of like an American state. That's very relatable because I'm American. And you know exactly what they mean by American state because American cultural hegemony. We've been over this. To illustrate, the set consisting of all even numbers between 1 and 10 would look like this: 2, 4, 6, 8, 10. These are two... I'm so bored right now. Are you guys bored? Are you all bored? Guys and gals bored? But what if we miss some? Let's just quickly scan through this to see, like, basically get a sense for how their relationship is going. Because this is the only thing that's got me, that's keeping my attention, is the incredible sexual tension between these two. I feel like he's doing a good job. I'm not sure what he's saying exactly, but it feels like he's doing a good job right now because she seems to really be into it. Functions. Uh-oh, he looks a little worried. Oh, but she looks okay with it. I think she's gaining more confidence in her tutor. I think that's what we're supposed to understand here. Look at her body language too. They're a little bit more, it's a little bit more forward facing. She was into it. Something happened here. Images. Sorry, I'm not reading any of this out loud. We're on page 48 of 63 of 267 right now. So it's like the functions undo each other. Linear transformations. Let xi and xj be two arbitrary elements of x. Let c be any real number, and let f be a function from x to y. F is called a linear transformation from x to y if it satisfies the following two conditions. This is confusing. Don't you think this is legitimately confusing for somebody in her position? Like, they just got done talking about how Japan is a set. Pictures. Pictures are great. The function f of x equals 2x is a linear transformation. That's because it satisfies 1 and 2. Feels good. 2x minus 1 is not a linear transformation. Oh my god, she looks crushed. But then she's all happy here. I guess this is just what she looks like when she's thinking really hard. I can relate to that. Are you all right? Yeah, don't worry. Phew. That's all for today. Thanks, Raiji. Oh, this is lore. Okay, we need to read this part, okay? So, I can't tell, is this directly after the tutoring session? They're walking. See their legs here. Raiji? Do you always eat lunch in the school cafeteria? Damn. I live alone, and I'm not that good at cooking, so most of the time, yeah. Well, next time we meet, you won't have to. I'm making you lunch. Huh? Don't worry about it. Tetsuo's still helping me out and all. You don't want me to? No, it's not that. It's just, On second thought, I'd love for you to make me lunch. Okay. Okay. I'm not sure how much more of this I can take. Okay. I make a lot of them for my brother too. You know, stamina lunches. Oh, how lovely. Combination. No. What the fuck is happening here? Why are they doing this? Is this going to arise in the next section? Oh, counting the number of functions? What? So, I understand the structure of this manga now. We start with these training sessions in the dojo, but then we go to the tutoring sessions, and I think there's supposed to be some parallel here. So if we want to truly understand what's happening in those tutoring sessions, I think we can more or less just take a look what's happening here. I put your backs into it. Yurino, don't rely on your hands. Use your waist. Osu. I thought he'd quit right away. I guess I was wrong. Ta-da! You must be really tired after all that exercise. Wow, but I could never eat something so beautiful. Hee hee, don't be silly. I don't know what to say. Thank you. Nom 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 nom. Awesome, so good, thanks. Misa, really, thank you. Don't worry about it. I feel a lot better now. Are you ready to begin? Sure, why not? Alright, boring. Boring stuff. Matrices aren't exciting as exciting as they seem in the movies. You know, yeah, no, just numbers, no Keanu. Why are matrices useful? Why is that? They're great for writing linear systems more compactly. Since they make for more compact systems, they could also help to make mathematical literature more compact. And they help teachers write faster on the blackboard during class. Well, those are some of the advantages. So people use them because they're practical, huh? She looks bewildered. Who gives a shit about practicality, right? It does look a lot cleaner. Not bad. Is anybody needing to read? Okay, listen. If you need to learn linear algebra, okay, don't do what I'm doing. Look at these diagrams carefully, okay? We're just trying to get to the juicier bits of the manga because oh, he's doing matrix multiplication now. You're right. Weird, huh? No, it's not that weird. Come on. Oh, look, she's holding it. Okay, wait. This is more stuff about cooking and how she's an absolute dream girl. Thanks again for lunch. I had no idea you were such a good cook. No problem. I'll make you another one tomorrow if you'd like. No, I wasn't trying to get you to. Don't worry. Don't worry about it. The best part of cooking something is seeing someone enjoy it. It'd be a pleasure. Thanks. What do you say? Ready for more matrices? Sure. No, they haven't been over vectors yet. It's all matrices. She's super impressed right now. Calculating inverses. Gaussian elimination and cofactor method. Oh, the denominator becomes 0. Okay. Determinants. This is linear algebra done wrong. This is a sin. Holding your fingers like this makes a good trick for remembering the formula. No, it doesn't. Is that a good... The tricky part is that minus. Why does that... I strongly disagree. And she's missing an eyeball. Incidentally, the area of the parallelogram spanned by the following 4 points coincides with the absolute value of the determinant. This is called Sarris's rule? Sarris's rule. Has anybody ever heard of this in their life? I've never heard of that. I don't know who Sarris is. I've never heard this before. Okay. Oh my God, look at this. Look at the innuendo here. Look at this. And then look at the signal he sends back. Nope. I'm not sure what's happening here. Might be very advanced, actually. Very advanced technique. Like, I don't know very much about this, but isn't like one of the strategies in like for pickup artists is to constantly reject the femoid as many times as, like, a lot, so that they become their deepest desire becomes, yeah, that's what it's called, nagging. That's right. Or is nagging like when you insult them? Maybe he's employing that sort of thing. Yeah, don't look into it, okay? Don't look into any of this. This is all disgusting, and it's all bullshit. But this is a thing. Oh my God, they're going over this. Are they going to talk about the permutation definition? They are. They're doing it. They're doing it. Are they going to talk about the sign of the permutation? They're doing it. Wow, they're the same. Good God. Stop. Stop. If this is on the test, I'm done for. Don't worry. Most teachers will give you problems involving only 2x2 and 3x3 matrices. Phew. I hope so. I think that's enough for today. We went through a ton of new material. Thanks, Raiji. You're the best. Time really flew by, though. Maybe I can... Maybe I can what? Do you need a bag for that? Why are we thinking about this guy? Jeez, look at the time. Oh. There shouldn't be anyone left in there at this hour. But there's Raiji. Where this newfound energy and determination, where is it coming from? Boring math. No one cares. Introduction to vectors. Pant. Put your back into it. Let's leave it at that for today. Wheeze, pant. More! I can do more! You can barely even stand. Ah! Just one more round. I haven't gotten stronger at all yet. Heh, fine by me. We're going to take a look at the vectors. Okay, so the vectors. Raiji, are you okay? Do you want to meet tomorrow instead? No, I'm okay. Just give me 5 minutes to digest this delicious lunch and I'll be great. 5 minutes later. Sorry about that. Ready? He's revived. Let's talk about vectors. Vectors are actually just a special interpretation of matrices. Really? Mini golf? Mini golf is a common first date, right? It's kind of like they're on their first date here. Although, no. I guess the other tutoring sessions would count as dates as well, right? Hey, it's Golf Misa. And it's Golf Tetsuo. Oh my god, there's so much math. What in the hell is this? Oh, it's supposed to be like span. Ooh, I'm beat. Let's take a break then. Good idea. By the way, Raiji, why did you decide to join the karate club anyway? Eh? Well, no special reason really. Hey, we'd better get back to work. Huh? Oh my gosh. Do you think there's some domestic violence at home? Is that what we should be concerned about? That's what's occurring to me. Linear independence and bases. Oh my god, linear algebra. Yes. This would also explain why he didn't want to go home after the tutoring session. This is getting dark. Never mind. Wait, she can just look at this and she knows. Oh, I guess it's 4 vectors. They touch hands once, Kappa votes. Once. One touching of hands. Wait, I've been thinking. It's kind of obvious that a basis is made up of 2 vectors, one in R2, and 3 vectors, one in R3. But why is it that the basis of an m-dimensional space consists of n vectors and not m? I think they've been operating on something else that I don't understand. It's the sexual tension that keeps us all the way through learning all this goddamn math. They're not going to do shit till the end, right? If they did it right here, if they fucked here and now, we'd be done. And we would deprive ourselves of all the great linear algebra to come. Remember, we haven't even scaled even a single one of the mountains. We haven't learned linear transformations. I mean, not really. Oh god, the sexual tension is insane. Of course. Oh, that's enough for today. Thanks for all the help. Let's talk about linear transformations next time. It's also an important subject, so come prepared. Of course. Oh, looks like we're going the same way. Legs again. Legs. No, I don't fucking recommend negging. Holy shit. Legs, though. Look at this. Fucking beta male. Look at this, though. He doesn't know what to say. He's got a frog in his throat. Come on. Oh, we get the answer. I really didn't answer your question before. Huh? I joined the karate club because I'm tired of being such a wimp. I want to get stronger. That way I can, well, I guess you'll be needing a lot more homemade lunches then. Wow. She really has really just one thing on the brain. What? Am I supposed to sing this? Does this mean music? To survive my brother's reign of terror, that is. Don't worry, I'll make you my super special stamina lunch extravaganza every week from now on. Thank you, Misa. Don't worry about it. Oh, sorry, I used the wrong voice. Oops. A practice match with not so I was not satisfied. To not be a wimp. What was that about? Linear transformations. Whoa. Fishy. Trigonometry? Oh, rotation matrices. Oh my gosh, are they doing projective transformations? Oh wait, hee, why should I worry? You're such a good teacher, Beam. You shouldn't worry either, you know. About the match? Oh, you heard? Yeah, my brother told me. Heh, thanks. I'm going to the gym after this, actually. I hope I don't lose too badly. Don't say that. You've got to stay positive. I know you can do it. Thanks. I'll do my best. I think we've got just one more section to get through here. He's doing it. This is the violence that I require here to keep my attention. Begin. He got kicked in the side. I have to win this. I've got to show them how strong I can be. Yeah! Enough. Nanhu University. Thank you very much. Damn. He lost. Sensei is stoic in the face of this loss. Good match. I'm sorry about the match. Yeah. My brother said you fought well, though. Really? Don't worry about... She's touching his hand. There's still a gap, though. You'll do better next time. I know it. I'm sorry, you're completely right. Sulking won't accomplish anything. Okay, this is the boring stuff. Eigenvectors and eigenvalues. Who gives a fuck? She is so pleased, though. Wait. This is very important. That was the last lesson. How did you feel? Did you get the gist of it? Yeah, thanks to you. Awesome. Really though, thanks for helping me out. I know you're busy and you've been awfully tired because of your karate practice. Not at all. How could I have been tired after all that wonderful food you gave me? I should be thanking you. I'll miss these sessions, you know. My afternoons will be so lonely from now on. He doesn't know what to say. Beta male. Well, we could go out sometime. Yeah, to what? To look for math books or something, you know? What the what's wrong with this guy? Look at this reaction. If you don't have anything else to do. Oh my god. Lonely men out there. Don't let don't let this manga poison your idea of women, okay? Please don't let this poison your idea of women. Now, I'm not saying that there are no women that are like Misa here. But this depiction, I have to say, it's a little bit problematic, as they say. Oh, this is their date when they're going to go look at math books. Looks like I got here a bit early. Hey there. Been waiting long? Right? Yeah. That voice. Aw, don't be like that. Look at these thugs. Stop it. Let me go. We just want to get to know you better. Misa! I have to do something and fast. Those jerks. He's surprised. Tremble. But what if it happens all over again? We're getting some lore here. I think the lore that we need to really understand the motivations of all of the characters here. All right? On my first date with Yuki, my girlfriend in middle school. Hey, let me go. We just want to hang out. I already have a date. Yuki! Those jerks. I have to do something. You! Stop it! Who are you? Kick. Gah. Haha. Seriously? One kick? What a wuss. These fuckers. These fucking fuckers. Look at him. analysts. Combinatorists. What are they gonna do to her? Time to go. Let me go. You there. Stop. Can't you see she doesn't want to go with you? Jeez, who is it now? Oh no! You're the legendary leader of the Hanamichi Karate Club, the Hanamichi Hammer in the flesh. Messing with that guy is suicide. Let's get out of here. Don't worry about it. But I think your boyfriend needs medical attention. Ha. Listen, I'm so glad you stood up for me, but it just wasn't enough. I don't think I can see you anymore. Wow. Wow. This is so fucking toxic. No. Okay. This does not get my stamp of approval. This whole fucking thing is... This is so toxic. Holy shit. I'm sorry. I couldn't do anything. Not this time. Oh my god. I'll show them. I'm so much stronger now. Come on, sweetie. Help. Yank. This time will be different. Let her go! Smack. What? Look at how happy she is. Look at this face. Look at this face. Come on, let's go. Raiji. Hey, stop right there. Just who do you think you are? Bath. Now, I've not looked. I'm trying to predict what this bath here means. Bath. Did Raiji... Is he throwing hands here? Well, actually, I don't know. No, it doesn't look like it. I don't understand what this bath means. I thought he was just going to be swinging at this point. Stay away from her. All of you. Haha. He thinks he's a hero. Let's get him. So this is measured, okay? He didn't just go swinging. He's giving them a chance to walk away. But they're not doing it. So what will Raiji do in response? What do you think? I mean, he's had training since this very unfortunate situation. Run! Be careful, Raiji. Look at this block. Bam. Oof. A left hand. You little. Thump. I can't tell what the fuck is happening here. It looks like he's getting kicked. Stop it. Please. Let me go. Stubborn, huh? Enough. Grab. Oh god, this guy again. He's cucking. He's making what is the phrase? He's making Raiji look like a cuck yet again. What's gonna happen? Attacking my little sister, are we? Tetsuo. Sensei. Oh, he's okay, wait. Violence. Oh, what am I supposed to say? Reiji? Am I supposed to say it like that? I don't know my own language. I'm sorry. Cock blocking. Yes. I don't like excessive violence, but in attacking Misa, you have given me no choice. What does this crack mean? Holy shit. What happened here? What is he cracking? Are there bones involved? Reiji? Reiji? Reiji, wake up. Is it Reiji or is it Raiji? Raiji, you're okay. Whoa. Wait, which one is it? Yurino, Misa told me what happened. Thank you. No problem. But I don't deserve your thanks. I couldn't help Misa. I couldn't even help myself the whole time. That's what this story's been about. You thought that this was about helping Misa with her linear algebra, but really this is about Raiji helping himself. I think we can see that now, right? I haven't changed at all. I'm still a weakling. Well, you may not be a black belt yet, but you're definitely no weakling. Putting Misa's safety before your own shows great courage. That kind of courage is admirable, even though the fight itself was unnecessary. You should be proud. But Raiji, he's right. I don't know what to say to you. Thank you, Misa. Thank you for look at this contact. He's blushing. And Big Brother. What the? I thought I was pretty clear about the rules. Huh? Oh my God, look at the way she's looking at him. Heh. Well, I guess it's okay. Misa's not a kid anymore. Thanks, Sensei. By the way, would you consider doing me another favor? Sure. I'd like you to teach me too. Math, I mean. What other thing could that possibly mean? There's not very many things he's accomplished in this manga. There's two things. He successfully taught Misa linear algebra, and he's figured out how to get Misa to touch him. Those are the two things here. What? He could really use the help. He could really use the help, being in his 6th year and all, if he doesn't graduate soon. So what do you say? It'd mean a lot to me too. Sure, of course. Great. Let's start off with plus and minus then. Plus and minus? Sounds like you'll need more lunches. The end. We did it. Oh, a little bonus frame. There you go. Okay. This I do not recommend. I recommend that we all erase this from our collective memories. Okay? This was bullshit. All right? This sucked. Not a fan. 0 out of 10. Yeah, not good. They never kissed. No, there was touching. Definitely nothing approaching consummation of the relationship. Okay? Furthermore, it's tremendously toxic throughout, okay? Do not get your ideas about gender relations from this text. More manga guides. Statistics, databases, electricity, physics, calculus, molecular bio, relativity, universe, biochemistry. Praise for the manga guide. Are all, so let's see. I wonder how many of these feature a dude teaching a female student. What do you think? Oh, you think it's the same? You think it's Raiji perhaps in all of them? Yeah, maybe. My favorite subject, universe. Universe. Yeah. Well. Okay, well, that was some worthwhile time spent looking at this absolute piece of trash. Okay. Just in case anybody wants, this is my name. Okay, but this is not me. I am not Iroha Inoue. Nope. It's not me. I don't know who that is. I want nothing to do with them. Don't know. Look like they're on a Go board, huh? Can't believe this. Alrighty. It's been very fun. I'm glad we got through that, so we never have to talk about it again. We learned never to look at the manga guide to anything ever again. Okay? So, I'm not looking at the manga guide to calculus, okay? Fuck rating anybody. I love you all so much. I'm gonna go eat some foods. Okay? Hope to see you again on a future stream. I'll do this again tomorrow, 1:30 PDT. Peace out, y'all. Have a great rest of your evening. See ya.